All right, so when we finished the first half of Unit 2, we had gotten through exponentials. So the second part, we're starting with logarithmic expressions because logs and exponentials go hand in hand. So to kind of make that abundantly clear, an important concept we have is that every operation has exactly one inverse or opposite operation, right? So if I have this x plus 3 equals 7 here, and I'm trying to solve for x, well, since this is addition, the inverse operation of addition is what? Subtraction, okay? I mean, that's something that we've known for a long time. We talk about it as the opposite. I don't know if you always use the words inverse, but they are inverse. That's what helps us solve equations. So what's the inverse of multiplication? Division. And with that, sometimes you'll try to do division at weird times when it's not actually multiplication. So like if I have sine of theta equals 1/2, and I'm trying to get theta by itself, I do not get to divide by sine because this does not mean multiplication, right? So I would have to do the inverse. It is better to say I don't have a clue what to do than to try and do division when it makes absolutely no sense, okay? All right, so then cubing. If I have x cubed equals 7, how do I undo that? Cube root, okay? Cube root. So then if I have exponentiation, which is a fancy form of the word exponential, so that x is up there in the exponent, I can't divide by 3 to get x out of there, right? I can't take the xth root because I wouldn't know what that is. So how do you undo exponentials? Logs, exactly. Logs. And that's why we're doing logs, okay? Goes on to say that recently, which is not really true because really you learned this stuff before you ever met me, but recently we reviewed this. We learned about exponential functions and their properties. If we want to solve equations involving exponential functions, we need an inverse operation. That's where our logs come in. So just like we can write rational numbers in decimal form, so 0.5 is equal to 1/2, we can write equations in exponential or logarithmic form. Probably the last time I'll write out that full word. We'll just call it a log. It's a lot easier. A logarithmic form. So these forms create equivalent statements that represent the same claim, right? Here's what that means. So back up here where we had this x cubed equals 7, if I take the cube root of both sides, that gives me that x is equal to the cube root of 7, right? They look very different. One has a cube, one has a cube root, but they make the same claim. In both sets of, or in both equations, things are equal. The relationship is still the same. So when this happens, or when you're subtracting, they still look very similar to each other. When you do that with exponentials and logs, it changes the way they look a lot more, and I think that's why sometimes we don't really comprehend the fact that it really means the exact same thing, just in a different form. Okay, so it does say we are not changing the problem when we convert back and forth. We are simply rewriting it, okay? So here's an exponential form, logarithmic form. A, B, and C that are in there have the same relationship in both of them, but they look very, very different. In both of these, the base is B. So the base of the exponential is the thing that has the exponent on it. The base of the log is the little subscript on the log to tell you what base it is. But either way, those are bases, okay? And then in this one, we have an exponent, and that one we don't. So our notes here can be that the base of exponential and log are the same. The base is the base. I mean, they look different in the different things, but it's still the base when we convert. Okay. So if I have the base of my log is 10, that's called the common logarithm. Okay, and it's written without a base. So if it just looks like this, there's no little subscript there on the log, it is implied that it is 10. It's kind of like when we have just x. It's implied that it's x to the first power. We don't write the 1. So here we don't write the 10. So it's understood to have a base of 10. So log of 3 is equal to log base 10 of 3. And up until pre-cal became AP, I would add to that statement, you never, ever, ever actually write it like this or see it like this. I probably even said that last year at this time. But then we got stuff from College Board, and it might have even been on the actual exam as well, where there was a log base 10, but they were actually writing the 10 in there, which I found very odd because that's really kind of never done. So I would have also probably said, don't write it like this, or they might not give you credit. Honestly, they probably would give you credit because they're writing it that way too. So what you really need to understand then, whether it's written like this or this, it means the exact same thing. I would imagine like in college, if you were writing it like this, your professor would probably be like, why are you doing that? So I'm not really sure why College Board thought that was a good idea. I'm sure they have a reason, but I have no idea what it is. All right, but either way, so now we're just going to convert. We're not solving for anything. We're not evaluating anything, just converting. These are exponentials. Now, do we all agree that 3 squared is 9? Nobody's going to argue with that, right? So the base of the exponential is 3. So we're going to do log base 3. And then here's the order that it goes in. 3, you go around the equal sign. 3, this is my 9. So log base 3 of 9 equals 2. And you're done. That's it. Okay. Then here, if I was going to write it, exactly kind of like I did here, this would be log base 10, go around the equal sign of y equals x. Okay. So that, again, probably not the best form. Like most of the time, I wouldn't write it like that, probably even if it was given to me like that. So, but I guess that's acceptable at this point now. But, and you could probably see it both ways. Those mean the exact same thing right there. Okay. All right, so for C, what is the base here? R. So log base R of what? W equals T. There you go. Now on D, there's two things that make this different than the rest. First of all, the exponential's on the right-hand side of the equal sign, which is totally fine. We'll just go around the equal sign the other way. And then we have E, which is not just not just a random variable like the R and the T and the W are, but it is the number that is like 2.717, whatever, right? So that changes things just a little bit. But let's go ahead and write it like we have here. So log, what would my base be? E. Yeah, log base E, and then we're going to go around this way of y equals 3x. Now this one, I can tell you, we're never writing it like that. Because when you do have a log base E, so if I have log base E of y, the log with the base E, that is a natural log. So it'll be the natural log of y. That is not a capital I, it is a lowercase n. Think of it as like log natural, natural log. English is always backwards, right? So natural log of y. So the way you would really write this is the natural log of y equals 3x. And then when you see the natural log, you just know that the base is E. Okay? What questions you got at this point? Okay, so now we're going to take the logs and we're going to rewrite them as exponentials. The base of the log is the base of the exponent. And you go around the equal sign again. 7 to the second power equals x. Which means x is 49, but nobody asked me to simplify it or solve it. It was just rewrite it, and there we go, it's rewritten. Okay. Everybody good with that? Okay, so what's the base of my exponential for b? 3. So I'm going to do 3 to the x power equals y. What's the base for C? 10. So I have 10 to the second power equals y. What's the base for D? E. So e to what power? The fourth, good, equals C. What questions you got? We good? All sounds familiar, right? Okay, good. So sometimes, not all the time, sometimes we can evaluate log expressions without the use of a calculator, okay? But not always. Sometimes we have to have a calculator to be able to really get what we need. But these first ones we're doing here, we can totally do it without a calculator. So I've got anytime I want to evaluate it, I think it's a good idea to make it into an equation. It just makes it a little easier. So we'll make this equal x. Just set it equal to x so that you have something to use when you rewrite it. Then we're going to start by rewriting it just like we did on the other page. So the base is 2. I do 2 to the x power equals 8, right? So the proper way to actually show the steps and solve this is that then you would get equivalent bases. So 2 to the x equals 2 to what power? 3, okay? Because 2 to the third is 8, right? So if 2 to the x equals 2 to the third, then x equals 3. And technically nobody asked me about x, right? But I said this is equal to x, and then when I said x equals 3, then it's all fine, okay? Everybody good so far? All right. So then here, I'm going to set again, that equal to x. So this is going to give me 5 to the x power equals 25. So you don't technically have to rewrite it as equivalent bases every time. I think for some of them, sometimes that is helpful. But what would x have to be here? 2. No, it's not necessary for all of them. Let's set this equal to x. So now I rewrite this as 2 to the x power equals 32. So 2 to what power gives me 32? 5. So x equals 5. Set this equal to x. What's the base here? 10. So 10 to the x power equals 100. So what does x equal? 2. Good. Any questions at this point? We're all good? All right, so let's continue on. Set that equal to x. So 16 to the x power equals 4. What would x have to be? 1/2, because that's the square root, right? Okie dokie, we're going to set this equal to x. So 3 to the x power equals 1. 0. Good. Take anything to the 0 power, you get 1. So x equals 0. What's the base here? 10. So 10 to the x equals 10. What does x equal? 1. Equals x. So 6 to the x equals 1 over 36. So I am going to rewrite this one as equivalent bases because I think for some people sometimes that might be a little bit more helpful to make sure you can wrap your mind around it. What do I have to do to 6 to get 36? I have to square it, right? And then how do I get that in the denominator? Negative exponent, right? Y'all answered the question backwards. But negative exponent gets the number in the denominator. The square makes it to 36. So then x equals -2. Okay. We all okay with that? What questions you got? Okay. So for this next one, so like let's just say that this was 15 to the x power equals 4. I couldn't have done that without a calculator, right? I would have to do something else. So these are ones that we couldn't do this way. We need to do them with a calculator. So I want you to open your tablets, go to Canvas. It's not an assignment like it has been because I didn't have a chance to do that because the link is different. But in the announcement for the class that says like Desmos AP link or something like that, click on that link to get you to Desmos. While you are doing that, I am going to show you a 3-minute video on logs.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Okay, so if my voice annoys you, at least I don't talk like that. But I do think that's a good video to kind of, even though we had to watch it a couple times, to kind of explain the logs and the fact that one little extra zero or missing one can make a huge difference, right? So let's just talk about, let's go type these in and let's talk about why. Well, actually, first, let's just talk about why this is different here. So I'm pretty sure when you went to the other link, or if you just go to desmos.com, I'm pretty sure it's blue. So this should be green because they have actually said now, this is the version you'll see on the AP exam. This is what's in Blue Book. So that's the link I'm going to change to the other things, but it'll stay in the announcements too. I don't think it's any different than the just desmos.com link, but just in case, we're going to use this one every single time. Okay, so if I want to find the log of, let's see, the first one is log of 9. Oh, and before we do that, one other little side note about decimals. I don't like changing rules and expectations along the way because I know things can get confusing. Had I known from day one that we were not going to use those inspires and we were going to go 100% Desmos, and that we would still at this point not have a way to store numbers in Desmos, I would have started the year differently with decimals. And so we have to be correct to 3. I always suggest you write down 4 because I tell you not to round, but I have two people that still insist on rounding, and both of them did it wrong on the last test. So don't freaking round, just truncate. But either way, if we can't store a number, and I always say never ever type the decimal back in because that's bad practice, but if that's our only option, if we use 5 decimal places to substitute in, then you are almost always guaranteed to be correct to 3. So my new rule for what I want us to be doing, I don't want you to write down every decimal place you see because that can get very daunting and then it can just be too much. And if you write down a wrong one, then you're wrong. You don't want to do that. So we're going to use 5. Okay, so again, I know that's changing midway and I don't like doing that, but it is what it is. All right, so if I want to find the log of 9, yes, we have this menu down here and you can click functions and stuff, but I don't like to do that if I don't have to. So you can literally just type log and then a 9 and it gives it to you. And then log of 6125 and it gives it to you. Okay, so let's just start by writing those two down. So that is 0.09542 and 4. I said 5 and didn't do it. 3.78710. Okay, and those were both just the common log, no special base, right? If I need to have base 2, like the next one, then I'm going to do log. How do we get to a subscript without having to go down to our menu? Do you know? Anybody? What? Shift underscore, exactly. So shift underscore or shift minus, it just pops it down there for you. And then we can put that 2 down there. Then if I need to arrow to the right to get back out of it, excuse me. And then I can put in my 10 right there. And then you can do the same thing, log base 7. So shift to get the underscore, shift minus, and then 7 and 2.52. Oh, no, 135. I was getting the answer there. Okay, and then write those down to 5 decimal places. Make sure you know how to type that stuff in. Any questions on how to type? Yes, ma'am. Dang it. Oh, thank you. Yes, you're totally right. The decimal goes there, not over here. I don't even really need the 0. Yeah, thank you. No wonder I thought I did 5 decimal places because I did, but they were wrong. Okay. Thank you. Anything else? We good? We can type that stuff in? Okay. That's really all you need your computer for, so you can shut it. Because there's going to be some more decimals in here, but I'm just going to tell you what they are. Okay, so now we're going to look at some logarithmic graphing, but differently than you have ever graphed a log, because we're not actually graphing the log. So one of the many useful purpose for logarithms is when dealing with exponential data. Okay, exponential data can be very challenging to display graphically because the values can start off very small, but it grows quickly. That's the whole idea of an exponential, right? And so it's difficult to create a display that effectively shows the quick change of this and what's going on at the very beginning. So here, these 2 graphs represent, there you go, the population of English Americans in the current United States since 1620, and it's grown exponentially. The estimated population is shown from 1620 to 1820, where t equals 0 represents the year 1620. So let's just talk about that sentence for a minute. Okay, not having anything to do with logs or exponentials. It is telling me that my input is the time from 1620 to 1820. But it also tells me t equals 0 represents 1620, which means my x values are not the years, right? My x values, if you look at your x-axis here, there's no 1620 here at all. So pay attention to that because that's something that has thrown y'all off, or some of y'all off, more than once when you were creating stuff with regression. Okay, so the graph on the left shows the population using a normal scale you'd be used to. We went from 0 to 200 years, And we got 1 million, 2 million, 3 million, 4 million, 5, 6, 7 million, just like you would put on a y-axis, no big deal. Exponential looks exponential. Okay, the one on the right, well, and you can tell that from 1620 to 1700, so like right here, you can't really tell that there was a change. It almost looks like at the beginning it wasn't changing at all, right? Which maybe that was the case, but it's actually not. On the right, it uses a logarithmic scale. So if you look at your y-axis here, it goes 10 to the first, 10 to the second, 10 to the third. The exponent's what's changing. So this is 10, 100, 1,000, 10,000. And so it's spaced very oddly. Okay, it's not spaced the way you would usually evenly space something because it's a logarithmic scale. And when you do it that way, we're still going from 0 to 200 years. When you look at the first 80 years, you can see that there actually was a great amount of change. Not only that, but there was huge changes here and here, right? And then the changes started going pretty much, you know, doubling or whatever was happening with your exponential. But by doing a logarithmic scale, you can see the early data a little bit better, and you can see what's going on with the later data. So here's the good news, is that we don't have to become super experts at the logarithmic scale. We need to understand what's going on. The one, maybe two questions we'd have over that is going to be multiple choice, so you will understand it well enough to where it should actually be an easy question. Okay, but I want you to have an idea of what's happening here. So this continues on to the next piece of paper. We're going to look at these same graphs again. So grab your other sheet of paper, and the same graphs are on the next page so that we can just continue talking about them. This is also going to go on page 71 when we're done. So the first graph is completely identical. The second one, I've added some x values here. Okay, we went past 200, 220, 240, 260, because they give us some info right here. It says the population of the English Americans in the current United States for 1840, 1860, 1880 is given in the graph below. Right? And we're going to plot those additional points over here, but we're going to do some stuff before we can plot them. So I have the population, 17 million, 31 million, 50 million, right? And if I tried to plot that over here, at 200 years, I was at 7 million. So when I go another 20 years, 17 million is way off my graph, and 50 is like way, way off my graph, right? It's not even worth it. But over here, I'm going to be able to make that fit. So what we're going to do is we're going to make this into make the data into a logarithmic scale. So maybe you can understand where it's coming from. So this row is the population and normal numbers that we're used to talking about. We're going to take the log of the population and put it in this row. So that means I'm going to take the log of 17,069,453, and I'm just going to tell you what it is. I know you can push buttons once you've done that a couple times. That's going to give me 7.2322, except that I'm only giving you 4 decimal places after saying I was going to do 5, because that's what I had written down and I didn't redo it. So, but it's fine. Okay, so the log of that 17 million is 7.2322. Now, those two numbers, not the same numbers, right? They don't represent the exact same thing. If I go to my logarithmic graph, 7.232 would be down here, so that's not what I'm actually graphing up there. Remember, if we're going to rewrite these in exponential, they mean the same thing. The base of that log is 10. So 10 to the 7.2322 power is 17,069,432. Okay, does that make sense for the just rewriting and converting? So this is the population. This is the log of the population. Then we're going to put the population in here again, but in a different form. 10 to the 7.2322 power. If I was to do that on my calculator, I should get 17 million back. Okay, so it's just a different form of the number. It's like putting, I can put 100 or I can put 10 squared. I can put 17 million, or I can put 10 to the 7th power, 7.2, whatever. You with me on that? So it's just a different way to represent the number. Again, you are not going to have to recreate this and do this again. If you can follow along with me and it makes semi-sense where it's coming from, that's really just what I want. So you don't think it's just this random obscure thing we're doing. All right, so then if I took the log of the 31 million, I would get 7.4975, which means when I put it in exponential form, that would be 10 to the 7.4975 power. And then if I took the log of the 50 million number, I'd have 7.7006. And I could rewrite that as 10 to the 7.7006 power. So the top row and the bottom row are actually the exact same numbers, just in a different form. Okay? So when I go back up here to plot those, when I go to the 1840, which is here at 220, this is 10 to the 7th right up here. So 10 to the 7.2 power would be just, or I'm going to aim the best I can, but it's hard for me to, maybe I'll move it down a little bit so I can aim a little bit better. And then when I do the 7.49, it's just a little bit more like that, maybe more, but it's good enough. It's good enough. I just want you to see that they just kind of follow along almost the same pattern as the rest of them do. And if you think about this being an exponential function, and it's real data, so it's kind of rough, but if I double 17, that's kind of close to 31. If I double 31, that's kind of close to 50. So we're almost doubling every 20 years, at least back then. But that's just a different way to look at it. And depending on what your profession is, what you're doing with this data, what you're trying to get out of the data, or what you want people to see in the data, one graph might be better than the other. But again, we definitely don't have to be experts on it. Okay? But we do have to understand it a little bit. We understand at least a little bit? Okay. And the way you're really going to see it is like in this next example here. So this weird looking chart, okay, and I'm all about transparency. When this became AP and this was one of the topics, I was like, what the heck is that? I've never seen that. But then I felt a whole lot better because I think literally everybody that is teaching this course, with maybe the exception of 1 or 2 people in the entire country, were like, what the heck is this? Like, we all had to go learn it and figure it out ourselves. Like, I didn't even know this was a thing. But it makes sense. I was able to make sense out of it, but I was like, I don't think this is anything I ever learned or ever saw. But so here again, we have a logarithmically scaled y-axis. So just like on the one up there, this is 10, 10 to the first, 10 to the second, okay? But they're just written out as 10, 100, 1,000. Also notice that on the y-axis, we're starting at 1. We're not even starting at 0. Your x-axis is normal, no biggie, all right? But your y-axis is logarithmically scaled. And the reason these lines look so weird is because this is 1, this is 2, 3, 4. Sometimes this board stresses me out. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like they start getting closer and closer together because that's how it works when you take the log, right? That's what's happening with those exponents. So you don't necessarily have to know how to create this. You have to know how to count it and how to plot points. I'm going to make you plot some points for the purposes of the actual exam. It would be a multiple choice question. But if you can plot them, you'd be able to figure out which ones were right. And the extra good news is the ones that I've seen, it's been like they give you your answer choices are different graphs. And if you kind of are just looking for this looking graph, if you have something that kind of looks like that, that's probably your answer. But may not always be the case. So let's look at this one. So I've got 1, 20, right? So 1 is still my x value. 20 is my y value. The way this works, this is 1, this is 10 right here. Since this is 100, so this is 1, 2, 3, 4. This is 10, 20, 30, 40, 50. This is 100, 200, 300, 400. See how that works? So if I'm going to plot the point 1, 20, go 1, that's 10. This is 20 right there. And this is A. even if you don't fully comprehend the whole logarithmic scale thing, if you can figure out points on this graph, you'll be fine. All right, so then 2, 300. I'm going to go to 2. So I go to 100, and then from 100, I go 100, 200, boom, 300 right there. We okay with that? Because this is 100, 200, 300. Alon, you with us? No, you're really not. Okay, then 3, 2. Here's 3, right? Remember, we start at 1, so this is 2 right there. So while I pass out the assignment, I want you to try and plot the last 2, and then I'll come up here and talk to you about them and about why the 15 might not really be exactly where you think it is or what you're used to doing. Okay, so let's look at 15, or the 4, 15. This, here I am at 4, this is 10, this is 20. So we would usually think that 5 would be halfway between 10 and 20. It's really not, because look at where 5 is here. This is 1, 2, 3, 4, 5. You see how 5 is like 3/4 of the way towards 10? So when you do that here for 15, it would really be more like that and not right in the middle. Now again, yes, I'm going to have you plot some, but I think they're all going to be so close that if it's multiple choice, you can figure out what's what. I don't think you have to worry about it being so like tricky or whatever. So that's D, and then E is at 5, 350. So here I am at 5. This is 1, 2, 3, 50, and again, I'd be like closer to the 4, but because that's such a small space, if you just put it in there, you can't really tell how far off you'd be anyway. So you're fine. Okay. What questions do you have? All right, tomorrow, your quiz. First quadrant, radian angles, and then tangent values. We can do that, right? Yes, good job.